Hello, and welcome to this presentation on uncertainty and interpretability in deep learning for medical image analysis. My name is Kristoffer Wikström, and this work is done together with my colleagues Mikael Kampfeier and Robert Jensen from the UIT Machine Learning Group and Visual Intelligence. So today we are going to talk about interpretability in deep learning. We are going to talk about uncertainty in deep learning, but our main focus will be on uncertainty in interpretability. Now, this is a topic that hasn't seen too much research, but it's actually very important if you want to develop trustworthy deep learning-based systems. Then we will look at a concrete application of our proposed methodology. And this application is segmentation of colorectal polyps. So, we start with interpretability in deep learning. Deep learning is the de facto standard for doing computer vision these days. But what is interpretability in deep learning? There are many ways to look at interpretability, but in this presentation we will look at interpretability as the explanation of a prediction. So, for instance, if we're talking about images, we want to know which pixels are important for a prediction of a model. Now, this ability is lacking from deep learning, and also a number of other machine learning systems. And these systems are typically known as black box classifiers. So basically, you have something come into your model, and then you get a prediction, but you don't know exactly what is important for that prediction. Now, as machine learning moves into domains where such interpretability is more important, getting methods that can actually provide explanations becomes more and more important. And that's also what we have seen, because recently there's been lots of recent development in interpretability techniques. So here I have an example to illustrate why interpretability is important. So in this case, we have a machine learning system that has been trained to classify images, and one of the classes in this dataset is horses. But the researchers discovered that the system had problems classifying horse images from a different dataset compared to the other classes. So they did this kind of explainability analysis. And what they noticed that when they did so, the horse was not indicated as being important for the prediction, but actually the tag towards the bottom left of the corner. So here on the left you can see the input to the system, and on the right you can see the explanation. So red indicates important pixels. It turns out that all the images of horses in this dataset contains the tag from the photographer who had taken the images of the horses. So the system essentially learned to cheat and didn't learn to recognize horses, but recognize the tag. Now, this example clearly illustrates how interpretability can be important to help us design trustworthy systems, both for us that develop systems, but also for people who intend to use the systems further down the line. Now, one domain where interpretability is especially important is in medical applications. So, very few clinicians will be comfortable making a prediction without any kind of interpretability. So if you're just given a number, most people would like to know what influenced that prediction. So here's another example to highlight why interpretability can be important. So in this case, we have these chest X-rays, and during this explainability analysis, they discovered that the system wasn't picking up actual features in the images that were corresponding to actual diseases, but it had figured out that images with this metal token up in the top right corner, as you can see here, which indicated different wards at the hospital, could be used to basically classify the images without actually understanding something in the images. So again, it shows that this kind of explainability analysis can help us to create trustworthy systems. Okay, so changing gears a little bit, we've talked interpretability. Now let's talk about uncertainty in deep learning. So uncertainty is a bit more intuitive. Essentially, we would like to know how certain a prediction is. Now again, this is something that can be very important, for instance, in the medical domain. If you just get a prediction, yes tumor or no tumor, most people won't feel very confident about that. But if you also get an uncertainty estimate with it, you might trust the model more. Again, this is something that's not present in deep learning as it is, but also here there's been a lot of recent work on creating deep learning models that can also model uncertainty. So here I have an example from one of our works that we will talk more about later, but I've included it to give you a taste of what uncertainty can do for us. So on the left we have the input to the system, and in this input we have what's called a polyp, which we would like to find. Then we have the labeled image, where a doctor has segmented out this polyp. Then we have the prediction of the model. And as you can see, it has been able to locate the polyp, but it has also indicated that other regions of the input is important for, or contains polyp. But if you now look all the way to the right, you can see the uncertainty estimates. So the correct polyp actually has low uncertainty, as you can see, but the incorrect polyp has very high uncertainty, as noted by the bright green color. So in this case, for instance, we could filter out uncertain predictions. And in that case, we would actually just be left with the correct segmentation. So this is one example of how uncertainty could be used to help us create more trustworthy predictions. Okay, so we've looked at interpretability and we looked at uncertainty. But what about uncertainty in interpretability? So what do we mean by uncertainty in interpretability? Well, essentially, we would like to answer the question, how certain is the explanation for a prediction? If we just accept an explanation as the truth without looking into how certain the explanation is, we might end up with a system that is not trustworthy, that we give it an unwarranted trust just because we have an explanation. So, for instance, here I have an example of an image classified as a cat, and on the right you can see the pixels that are important for classifying this as a cat. So, as you can see, the ears and the eyes and the nose and parts of the body are being highlighted as important for the cat class. But the question is now, are all of these pixels equally important, and are all of them equally certain? So maybe there are some parts that are more important for the cat class or some parts that are less important. But in the general explainability frameworks that exist, there is no way of answering this question. And in general, there's been very little work on answering such questions. So that has been our goal in the work we will look at now, to try to model the uncertainty in explanations. So we will look at this from the application of segmentation of colorectal polyps. So the rest of this presentation will be based on this work that you can see at the bottom of this slide. So again, the task is segmentation of colorectal polyps. And now these are growths that can be found in the intestines of people, and you would like to find them because they can develop into tumors that can give you cancerous tumors. So we had several goals here. We would like to segment out polyps. We would also like to identify which pixels are important for locating the polyp. And then we would also like to measure the uncertainty in the explanations, as I explained on the previous slide. So here is an example of how the data might look. You have an input of the intestines of a person's, and then you have the label, which are given by a physician. So first we looked at how to get the explanations for the predictions. And in this work we've been looking at a method called guided backpropagation. So I won't go into too many details on how this method works, but the essence is that we are looking at the gradients of the neural network to get explanations. So essentially, you pass the image through and get the prediction, and then you calculate the gradients using the backpropagation algorithm to get an indication of which pixels are important for the prediction. And then in the guided backpropagation procedure, you also do some additional steps in the backpropagation, namely zeroing out negative gradients to get clearer explanations. So if we look at how this looks, on the left we have an input and we have a label, and then you can see we have the prediction of the model. So in this case, it looks like everything is good. The prediction is the same as the label. But if we now look at the interpretability maps all the way over the right, you can see that we have this additional green area marked as important up here. So green pixels here indicate that they are important for the prediction. Now in this case, if you did not have the correct label and you were an experienced practitioner, you wouldn't be sure if, okay, are these pixels we actually need to investigate further? Do we need to look into the patient more? Or are these explanations as certain as the one towards the bottom right of the image? And using the standard explainability frameworks, you cannot answer this question. So that is what we set out to try to develop a new methods to be able to address the uncertainty in explainability. So in our paper, we proposed a method which we called Monte Carlo guided backpropagation. So this is based on an uncertainty method that's called Monte Carlo dropout, proposed by Gal and Garamani. So dropout is usually a regularization technique that is used during training of neural networks. And in essence, you're dropping connections in the neural network. So basically adding noise to the system. And this is to create a system that is robust to noise and do not overfit to the training set. Now the idea of Monte Carlo dropout is to also use dropout during inference. So essentially you take the same image and you pass it through your network several times, but you keep dropout on during inference. So essentially you're sampling more and more predictions, but with noise in it. What we propose is to use this Monte Carlo dropout procedure, but instead of just looking at several predictions, we also get an explanation for each of the predictions. And based on this, we can get uncertainty in the explainability. So here we will have a look at how this will work. So assuming we have an already trained convolutional neural network that gives us some predictions. First, we take an image and pass it into the model, and we also have some noise induced into this model. That will give us our first prediction. Then we take the same image and add new noise, which will give us our second prediction. And we do this again to get our third prediction. Now, for each of these predictions, we now get an explanation. And based on these explanations, we can take the standard deviation across all of these three explanations. And that will give us the uncertainty in the explanations. Okay, so let's see how this procedure can be used. If we now look at the same example that we were looking at earlier, we see on the left we have the explanations without uncertainty, and on the right we have the explanation with uncertainty. So, as you can see here, green pixels indicate that parts of the image are important. But when we also include uncertainty, you can see that now parts of the image is being highlighted as red. So on the right, green pixels indicate pixels that are important and also certain, while red pixels indicate that the pixels are important, but we are very unsure if they are actually important. So in this case, when you use this Monte Carlo guided backpropagation, you will actually see that the pixels corresponding to the incorrect prediction, or the pixels towards the top left of the image here, are actually very uncertain. So you wouldn't take them into account maybe if you were analyzing this image. Let's look at another example of how this Monte Carlo guided backpropagation can be used. So we have another example here. On the left you have the input, then you have the label, and then you can see that in this case the model makes a good prediction. So the polyp is segmented correctly. But if you look at the explanations over to the on the right hand side, you can see that okay, the polyp itself is being highlighted as being important, or pixels associated with the polyp. But we also have these green specks towards the left here. So again, if we didn't know the true labels, maybe you would be confused by these additional explanations and you would be inclined to investigate further. Okay, so if we now use our proposed method to try to model the uncertainty in these explanations. So again, on the left we have without uncertainty, and as I said, we have these green specks over here that are highlighted as being important for the prediction. But if we now look at the right hand side where we include the uncertainty estimates, we can see that most of these pixels are actually again highlighted as being uncertain, while the pixels associated with the actual polyp are green, so meaning that they are certain and they are important. And we also see that towards the bottom of the image there are some pixels that are highlighted as important but actually are very uncertain. So again, this illustrates how modeling uncertainty in explainability is important to create reliable deep learning models. Okay, so that brings us to the end of this presentation. If you would like to know more about our work, feel free to contact me at this email address. And if you would like to read the full publication that this presentation is based on, you can have a look at this uncertainty and interpretability in convolutional neural networks for semantic segmentation of colorectal polyps, published at Medical Image Analysis. Also, if you would like to see similar works but for clinical time series, we have a recent paper called Uncertainty-Aware Deep Ensembles for Reliable and Explainable Predictions of Clinical Time Series, where we also do something similar as in this presentation, but instead of looking at medical images, we look at clinical time series. So with that, I would like to thank you for your attention, and I hope you enjoyed the presentation.